Good morning, everybody. Thank you for coming to my talk. One clarification, I'm technically from UF. Jessica Meloy, one of the second authors, is currently at Boeing. So I'm going to be talking about some of the work that we've done at UF, working on developing an instrumentation-grade wall shear stress sensor for use in wind tunnel facilities. And so one of the questions you might obviously ask is, why do we want to care to measure shear stress in the first place? And your answer might include things such as making fundamental fluid measurements. There's a lot of different especially complex flow fields that are still not very well understood in the fluid dynamics community. You could also use it to make a friction velocity measurement, which is needed in normalization of boundary layer data. Used as a tool in the quantification of drag mitigation efforts, or perhaps as a tool as a feedback mechanism in flow control situations. Currently, methods for measuring shear stress include indirect and direct methods, where indirect is generally either traversing hot wire probe or PIV, where you're doing a velocity field estimation and then doing a fit to the wall to get some estimation of shear stress. But it's always based on velocity. It's not a direct measurement. Direct tools include folding element and micropillar approaches, but unfortunately at this current time, there is no commercially available tool that can do direct time-resolved measurements in complex 3D flows. Part of the reason for that is some of the requirements of this kind of measurement include being highly resistant to pressure. In turbulent boundary layer areas, your pressure forces are often 3 orders of magnitude higher than shear. But because it has to be a directly exposed sensor, if you're doing a direct solution, you have to be highly resistant to that kind of cross-axis input. Additionally, there's a number of different temporal and scaling and spatial scaling requirements to do full resolution of turbulent boundary layers. The 3 key metrics include the front side smoothness, known as hydraulic smoothness, basically how rough is your front edge so that you're non-disturbing to the flow, the characteristic length scale of your primary sensing element, and also the bandwidth, of course, of your sensing device. And for a kind of a low-speed characteristic boundary layer flow of, say, RE theta 2500, those limits would be about 100 microns in smoothness, 400 microns for your floating element size, and 12 kilohertz of bandwidth. And that's for full resolution of all the turbulent scales. So our solution to this problem is developing a direct MEMS capacitive shear stress sensor. You can see the structure in the top right. It's a picture of the fabricated device. It's very similar to a lot of capacitive accelerometers in structure, where you have a floating element or a proof mass in the center. It's supported over the substrate by a series of flexures. In this case, it's a very simple H-bar structure. And on either end of the device, you have interdigitated comb fingers, in this case set up in a differential position, which helps us with the directional measurement aspect of it. And so, of course, this flow comes across the device up and down tangentially, going to impart a surface force, which is going to give you a bending of the tethers, change displacement of the gaps, variable capacitors, right? So traditionally, in a lot of accelerometer applications, all you care about is an AC input. So you can apply a DC bias, not a problem, measure your output, and you're good to go. In this case, because we care about measuring both mean and fluctuating shear stress simultaneously, it's important that we do a modulation approach to get that out from the capacitors. In this case, amplitude modulation approach, we simply bias each side with a 180 degrees out of phase carrier signal. We use 1 megahertz, and that helps us to modulate the information from the baseband up to the carrier signal, where any change in mean shear stress is going to manifest as a change in the power at the carrier frequency bin, right, at 1 megahertz. We also go ahead and with our circuit do demodulation in real time. And what this does is, because our circuit is, and our whole system is integrated, that allows anybody that's using it to just hook up their DAC at regular low speed and sample the baseband with no problem. They don't have to do any high speed sampling or anything like that. So kind of a block diagram of what that circuit looks like is right here. We have an onboard Colpitts oscillator, generates a modulation bias. Traditionally, we use 1 megahertz and 8 volt amplitude. We have a timing control block. This is linked to that carrier signal. It generates a square wave that controls our rectification, our active rectification switch. And this allows us to retain the phase and directional information, I'll get a little more into that later, of the actual baseband information. We do an active rectification switch between the buffered and inverted signal back to do our envelope detection. And then, of course, low-pass filtering at the output, and that gives rid of our high-frequency residual and gives truly just the baseband return to the DAC system. So what does this look like? This is kind of a picture of the package sensor in the top right. You can kind of see the die and it's centered in the middle there. The tube itself is 1/2 inch diameter, 2 inches long, stainless steel. Inside is a buffer amplifier. Co-location of this amplifier right behind the die allows us to separate the electronics much further back without any significant signal degradation from the high output impedance device. The device itself kind of sits on this PCB cap that's recessed into the end. And then there's a laser machine shim cap that gets placed around. That helps us meet that hydraulic smoothness requirement. So once we have this all packaged and put together and calibrated, and we can provide it to other people at other institutions, all they have to do is plug in this box to the wall, put in the shear sensor into wind flow, and hook it up to a baseband DAC system, and it's ready to go. It's all contained. So that's all well and good. How does it perform? This is what we call the DC drift test, or it's somewhat our DC noise floor, if you will. It's looking at what the variations in the DC output of the circuit are over time with no flow input whatsoever, just sitting on a table. We end up seeing that our drift is on the order of 0.2 millivolts per hour, which corresponds to error of about 0.1 Pascal per error for DC measurements. In terms of noise floor, it's just over 800 hertz. And again, you can see it up to 10 kilohertz here. Some particular points of interest might be at 100 hertz or 1,000 hertz. The corresponding minimal detectable signal ends up being about 340 micropascal at 100 hertz and 120 micropascal at 1,000 hertz. So how do we calibrate the actual performance of this device? We have two methodologies. One is for mean shear and one is for fluctuating shear. For the mean shear, we use what's called a laminar flow cell, and this is basically just a Poisson flow-driven pressure gradient and a duct. We can adjust the shear measured at the wall according to this equation here, where h is just the gap height of this laminar flow. Then we can use a mass flow controller to adjust the flow, measure our pressure gradient, linear pressure gradient about this sensor, and back it out to an estimate of shear. What the results of that look like, you can see on the x-axis is the estimated mean shear from that simple equation on the last screen, and the DC change from zero offset here on the y. We do a linear fit to this data. We see there's very low residual. We end up with a sensitivity to mean wall shear stress of 3.44 millivolts per Pascal. So I mentioned directional measurement earlier. What we're doing in this test is taking that same laminar flow cell, having our device input in one orientation. Let's start with the red first. It's called 0 degrees. Taking the flow controller and ramping it up and then ramping it down to different flow cases. So you can see the step response is the step response as we change that flow speed. Then if we take the sensor, rotate 180 degrees such that the relative flow is now headed in the opposite direction across the sensor, and repeat that test, we end up seeing is basically almost a perfect mirror of that step thing. So what that's letting us see is that the mean flow is representing as a change in the DC output, and that's from the demodulated carrier signal magnitude. So we can also do fluctuating wall shear stress characterization. We use this using an acoustic plane wave tube. It's pretty simply just a speaker or a compression driver at the end of a sealed tube. By driving at some frequency, we establish an oscillating pressure and velocity gradient within the tube. We can locate the shear stress sensor at a quarter wavelength node away from the termination. What this allows us to do is place it at a velocity maxima and a pressure minima. So that helps us isolate the actual response to true shear and not pressure forces. We place a reference microphone at the termination with a sensor plug in the side, and we're able to solve for the estimated shear stress. This is just a solution of the Stokes oscillating problem, Stokes' second problem. Shear stress estimation is here, linearly related to that P measured at the termination. So again, we kind of repeat the same procedure where we increase the pressure. The input frequency in this case is 1.128 hertz. We see at the bottom left, you can kind of see the roll onto the noise floor here. It's a little non-linear, but once we get above the noise floor of the device, we have a nice linear regime between shear stress and voltage. And we end up, if we do a fit to that region, we get a shear stress sensitivity of 3.45 millivolt per Pascal, whereas the mean was 3.44, so well within our error bars on either of those. So again, for the directional measurement, this plot takes a little explaining. What we're looking at here on the x-axis is, again, shear stress. This is going over those sensitivity measurements. On the y, we're looking at the phase lag, the relative phase lag between the shear sensor and that reference microphone at the termination. And so what we see is at, say, 0 degrees, we can start in red here. It's relatively constant, that phase lag between those two transducers over the course of the sensitivity calibration. If we rotate it about 45 degrees, so it's slightly off axis, we still see that condensed phase follows along nicely. We're still having flow direction the same, or flow information going in the same direction. But if we rotate it 180 degrees, so now we're going in the opposite direction again, we see that our phase is shifted. Our relative phase is shifted 180 degrees. So this means that we can retain both directional information for DC and AC content if you sample and have a reference transducer. And of course, at 90 degrees, when it's off axis, it's totally incoherent. So we can do a frequency response function. We generate this by basically having a movable end wall that locates our sensor at that quarter wavelength node for various different frequencies. We perform the sensitivity test at all of them, and we can generate this nice plot up here. You see your resonance is roughly around 3.5 kilohertz, a little lower than we'd like. But our usable flat band, from the plus or minus 3 dB standard, extends out to about 2 kilohertz, right about here. And coherence is good, and phase, of course, is for transition, 3.5. So it's all well and good on the desktop. How does this actually perform when we are in a real wind tunnel outside of our controlled environment, right? So we've gone to a number of different facilities. One of the facilities we went to is NASA Langley Research Center, and they're known as curved duct test rig. We see here it has a rectangular cross-section on the interior. You can kind of sort of see the shear sensor is inserted here, a little white dot in the sidewall. Flow, it's an open loop facility, so flow is pulled from the outside, which is a little interesting. So it's In Virginia, it's very hot and humid, so our sensor's kind of exposed to that. It's not controlled. We're able to do moderate flow speeds from 0 to 0.5 Mach. We can do different acoustic excitation as well on top of that to see if it responds in any interesting way. And so the couple of plots I'll get into from that test are one for the mean shear response. Again, this is just looking at that DC voltage output. We go from 0 up to 0.5 Mach and then back down. This is very encouraging to me because it's hard to see because they're so closely aligned, but in blue is the ramp up and red is the ramp down, and they essentially fall exactly on top of each other, which means that in the actual flow condition case, we have almost zero hysteresis shown. At the bottom, you see a little bit of hysteresis, and that's probably due to this environmental conditions, a little temperature and humidity response, because we're drawing that outside air, and that changes over the duration of the test. Again, we can see the AC content. So this is, again, simultaneously sampled. We just take the output of the one box, split it into a DAC and a DMM. We can get the AC content here. And again, you're looking at stepping from Mach 0 to 0.5, 0.1, and so forth. And again, you can see that the kind of energy content that you'd expect in the flow to increase. We do see that in the response. We test a couple different conditions of the wall itself. I won't get into the details, but just to say that the wall condition changed, we have to totally take the test apart, put the sensor back in, reassemble everything. And when we rerun it, we see that the relative magnitude is almost exactly the same. And it should be a little different, but because it's so similar, that gives us confidence in the repeatability of this measurement over multiple tests. This kind of roll-off that you see here, those are my fellow fluid people, will know that as kind of the roll-off in the turbulent energy cascade. It would, in theory, keep continuing down, but because we have this resonant spike, it gets pulled back up. But seeing this nice roll-off is very important for being able to elucidate what's going on in those turbulent energy scales. So, in summary, we've been working on a silicon micromachined differential capacitive shear stress sensor. We have a calibrated sensitivity of roughly 3.5 millivolt or 5 millivolt per Pascal. Dynamic range has been calibrated up to 80 dB. It, in theory, is much higher, but we don't have a calibration rig to kind of test the nonlinear upper limit. Our pressure rejection has been calibrated at 72 dB. It's a nice small form factor with a compact integrated circuit, and we have good qualitative agreement with comparative measurements in multiple facilities by now. Some of the things we're looking at going forward is increasing that smoothness by using through silicon vias or other backside electrical contacts, doing smaller floating element sizes and higher bandwidths, of course, and then looking at two-dimensional shear stress. So instead of a single direction, having a true vector measurement at that surface tangible force. I'd like to thank the funding agencies, of course, primarily NASA and AFOSR, and of course, all my good friends at IMG who I work with. And with that, I will take any questions.